Hello everyone, this is Niteen Mohod and today we are going to see hexadecimal number system and interconversions. As you all know, hexadecimal number system is a number system which uses 16 different symbols to represent any number and therefore its base or radix is 16. The 16 different symbols it is using are 0 to 9 and A to F. Decimal and hexadecimal numbers are same till 9 decimal. But from 10 decimal it will come A, for 11 it will come B, likewise for 15 it will come F. From the table it will be very clear. Here the decimal numbers are shown up to 9, the decimal numbers and hexadecimal numbers they are same. But from 10 onwards, here comes A, B, C, D, E and F, and this is the hexadecimal number system, or these are the different symbols which are being used in hexadecimal number system. So far the binary equivalents are concerned, the highest number in hexadecimal number is F. F is represented as 1111, and from 9 itself we are representing all the hexadecimal digits by 4-bit binary. But here 0 can be represented as single 0, 1 can be represented as single 1, but to maintain the uniformity this can also be written like this by adding zeros on the left hand side. So we can write 1 as 0001, 2 as 0010, 3 as 0011, likewise. So every hexadecimal digit is represented by 4-bit binary, and decimal numbers and hexadecimal numbers they are same up to 9 decimal only. Thereafter they change or they differ. Now decimal hexadecimal conversion. The weight or weights associated with different digit positions in hexadecimal number systems are as follows. Suppose some number is given, some hexadecimal number is given to us with hexadecimal point like this. So from the point towards left, that is towards MSD, the weights of the hexadecimal digits will be 16 raised to power 0, 16 raised to power 1, 16 raised to power 2 and 16 raised to power 3, 4 like this. Towards right from this hexadecimal point, the weights will be 16 raised to power minus 1, 16 raised to power minus 2, 16 raised to power minus 3, so on and so forth till LSD. Here we have written actually the values of 16 raised to power 0 as 1, this is 16, this is 256, this is 4096. Similarly on this side, 16 raised to power minus 1 means 1 upon 16, that is 0.0625. This is 1 upon 16 square, that is 1 upon 256, that is 0.0039. Then 16 raised to power minus 3 means 1 upon 16 cube, that is 1 upon 4096, that is 0.00024. Likewise, we can go towards LSD. Hexadecimal to decimal conversion. This is the first kind of conversion we are seeing here, where the weight concept will be used. Hexadecimal number can be converted to its equivalent decimal by taking the positional weights, as we have taken here, of each digit in a given hexadecimal number from LSD to MSD and then adding them. So how it is done, that we are going to see. The number, hexadecimal number which is given is 121 hexadecimal, and we are to convert this 121 hexadecimal into decimal. So first step is, now here this is not the fractional hexadecimal number, so this will be called as LSD and this will be called as MSD. So starting from LSD and going to MSD, we'll have to take the weights like 16 raised to power 0 for this digit, 16 raised to power 1 for this digit, 16 raised to power 2 for this digit, and multiply them column wise and add them row wise. You have to add this with this, and the addition, total addition of this will be added with this. So when we will do it, we will get 16 raised to power 0, that is 1 into 1, you will get 1. This is 16 into 2, that is 32. 16 square into 1, that is 256, and when you add them, you will get 289 decimal. Now we will take one more example where the fractional hexadecimal number is shown, that is 41.14 hexadecimal, and we have to convert it into equivalent decimal. Now we will have to use this point that as a decimal point. So this point will be treated as, hexadecimal point. And from hexadecimal point towards left side, we will have to use weights like 16 raised to power 0, 16 raised to power 1. Similarly, towards right, for this 1, 4, we have to use 16 raised to power minus 1 and 16 raised to power minus 2 as the weights. Therefore, when we will do it, this is the point which is given here. Then for this one, 1 into 16 raised to power 0 in one bracket plus 4 into 16 raised to power 1 in second bracket. This is the hexadecimal point as shown here. Then 1 into 16 raised to power minus 1 plus 4 into 16 raised to power minus 2. When we will solve all these brackets and when we make the addition of them of the left hand side, of the right hand side, we will get finally 65.0781 decimal. So this is decimal equivalent of 41.14 hexadecimal. Then decimal to hexadecimal conversion. This is a simple method and we are using it everywhere, because while converting decimal to binary, we have divided the decimal repeatedly by 2. While converting the decimal to octal, we have divided the decimal repeatedly by octal's base, that is 8. Now here decimal to hexadecimal, it means we are repeatedly going to divide the decimal number by the base of hexadecimal, that is 16. So decimal number is repeatedly divided by the base of hexadecimal. The quotient is brought down and the remainder is written to right. Remainder you have to write every time during every division. Quotient you will have to brought down and remainder you will have to write on the right hand side. Division is continued till the quotient is 0. First remainder will be treated as LSD, that is least significant digit, while the last remainder will be treated as most significant digit. Now through example it will be more clear. So obtain the hexadecimal equivalent of 96 decimal. It means we'll have to obtain the equivalent hexadecimal number for the 96 decimal. Now the procedure is what? Decimal number is repeatedly divided by the base of hexadecimal. So as per the method, 96 decimal will be repeatedly divided by the base of hexadecimal, that is 16, till the quotient is 0, with remainder written every time on right side to make the equivalent hexadecimal as follows. Here 96 we have divided it by the base of hexadecimal. Now 16 6 are 96, so remainder will be 0. Then we have brought this 6 here. Now we cannot divide 6 by 16 because we don't want the result in fraction. Therefore we have written 16 zeros are 0 and 6 remainder as it is. Now the remainders which we are getting here, 0 and 6, they are to be taken in upward direction. So we will get the equivalent hexadecimal for 96 decimal will be 6060 hexadecimal. Then conversion of fractional decimal to hexadecimal. For converting the fractional decimal to hexadecimal number, the procedure is almost reversed. Reverse means what? Instead of repeatedly dividing, we have to multiply. So instead of dividing repeatedly, the fraction is, or the fractional part is multiplied by 16, that is the base of hexadecimal, and the carry is written separately and did not taken in the next multiplication. We'll see it. Finally, all the carries are taken from top to bottom to get the equivalent hexadecimal for the fractional decimal. See here, the example given is convert 0.3 decimal to its equivalent hexadecimal. Now in order to convert 0.3 decimal to its equivalent hexadecimal, we'll have to multiply this by the base of hexadecimal. So 0.3 multiplied by 16, we will get 4.8, and 4, which is the number before this point, will be treated as carry, so with carry of 4, and 0.8 will be taken in the next multiplication as 0.8. Then 0.8 multiplied by 16, that gives us 1.28, where 1 will be treated as a carry, 0.28 will be taken here. 0.28 multiplied by 16, that gives 4.48. 4 will be treated as carry, so with carry of 4, 0.48 taken here, and after performing multiplication, we will get 7.68, where 7 will be treated as a carry, and 0.68 can be taken to the next place. But if the division continues, if the multiplication continues, we have to stop maximum up to 4 steps. That is appreciable, and therefore all these carries which we got 4147, they are to be taken in downward direction, means the number you have to write like this. So equivalent for the fraction is appreciable maximum up to 4 digits as we have done here, and therefore 0.3 decimal is equivalent to 4147, that is 0.4147 hexadecimal. Then hexadecimal to binary conversion. We have already cleared that each hexadecimal digit is represented by the 4-bit binary number. So for converting the hexadecimal number into its equivalent binary, each hexadecimal digit is replaced by its 4-bit binary equivalent. Space is kept between the successive groups of 4-bit binary equivalent. Here, as an example, the hexadecimal number given is 739FB. This is the hexadecimal number with base 16. If we want to convert this number into binary number, so for each hexadecimal digit, we'll have to write 4-bit binary. So for 7, it is actually 111, but since hexadecimal digit is represented in 4-bit binary, so we will add 10 on the left hand side and we will write 0111. Similarly for 3, 0011. For 9, it is already 4-bit 1001. For F, 1111, and for B, 1011 binary. So this entire number with base 2 is equivalent of this hexadecimal number. Similarly, the fractional hexadecimal number can be converted like this. Here now the fractional hexadecimal number given is 56D.2C, a hexadecimal. In order to convert this, again we'll have to write for every single hexadecimal digit, we'll have to replace it by 4-bit binary. 5 is actually 101, but it should be 4-bit binary, so we have added 10 on this side, so 0101. For 6, 0110. For D, it is 1101. Then point will come. Now this is binary point and this is hexadecimal point. For 2, 0010. For C, 1100. And for A, 1010. So this is how the hexadecimal numbers can be converted into binary directly by making the group of 4-bit binaries. The last conversion is binary to hexadecimal number system. So what is to be done? You should start always at the binary point, because the fractional number which is given, which is a binary actually, binary fractional number, when given, we have to start at binary point, make the group of 4 bits in both the directions from the binary point, towards left till MSB and towards right till LSB of the given binary point. While grouping or while making the group of 4 bits, there are the chances that you may left with 1, 2 or 3 bits short. At that time you can add the necessary number of zeros and you can make the group of 4 bits. For example, if you want to convert this number to its equivalent hexadecimal number, here I will have to make groups like this, from this point towards left and from this point towards right. We are making the group of 4 bits, so 0101, this will be one group, then 1011 will be second group, then 01 only is there, means it is short of 2 bits, so we will add 2 zeros here on this side. Similarly on this side, 1111 is the first group. For second group I will have only one here, so I will have to add 3 zeros here. So on grouping 4 bits from binary point towards MSB, 2 bits fall short and 3 bits fall short towards LSB. Therefore, adding required zeros on respective sides and grouping 4 bits, we will get this situation that 0101, 1011, 01 was there. We have added these 2 zeros on this side so that the group of 4 bits can be made. Similarly on this side, 1111, this was the first group. For second group, only one single one was there, so we require to add 3 zeros here, right? Now we will write the equivalent hexadecimal digit for each group. So 1010 will be called as A, 1101 is D, 0010 is 2. Here on this side, 1111, that is F, and 1000, that is 8. So 2D AF8 hexadecimal, this is the hexadecimal equivalent of the given binary number. This is how the conversion is to be done. I hope the idea of hexadecimal number system, their interconversions, positional weight concept, conversion of hexadecimal to binary, binary to hexadecimal. Everything is clear to you from these slides. Thank you.